Oh, there's no sound. Now there's sound. I've been lecturing for a half an hour and there's been no sound. I'm going to kill this and think about what I'm going to do. Thanks, Mutab. I may jump out of the chat and restart over. Okay, we're going to try this again, and it looks like it's actually recording my voice. I just talked for 45 minutes with no recording. I hate Blackboard. This software system is, yeah, interesting at best, and I'll just leave it at that. Okay, so let's do this again. So I've learned a lot in the last 45 slides. And you don't actually have to be here, but thank you for letting me know that the recording wasn't happening. And so I'm going to jump through this so you can sit out here if you'd like. Otherwise, I'm giving everybody attendance credits because I was actually traveling all week this week. And so if you want to jump out at any point in time, no worries. Other than that, I'm just going to walk through this, but there will be a recording out here that you can play back at your convenience. Okay, so we're going to talk about virtual memory management, and by that we're going to take a look at and drill down into the algorithms that occur to allow us to perform virtual memory management operations. And so we've had, in the first cases of operating systems, we knew that a program had to reside in memory and its data had to reside in memory before it could execute. And then we wanted to run multiple programs at the same time. When a single program was in memory, it just had to protect itself from itself. And we really didn't care if it overwrote memory locations because it could only impact itself. But when we had multiple programs in memory, we didn't want one program to be able to impact the efforts of another program by writing over memory that the other one needed. So we needed protection schemes. Then we had the issue of RAM was expensive. And so we only had so much RAM, and if we were going to run multiple programs, it would be nice if we had kind of a perception that we had more RAM available. And so that meant we could utilize a secondary store, meaning a disk originally, but today that secondary store is becoming flash memory, and a lot of Macs don't even have disk anymore, they just have flash memory. A lot of phones don't have disk anymore, they just have flash memory. So that secondary store is a slower, less expensive memory location. And so our virtual memory management process, the things that the operating system does, is controlling how do we move things between RAM and that secondary store, regardless of if it's disk or if it's flash memory, so that we can optimize our use of memory across all the programs that we're running, and give each program the illusion or perception that it has almost unlimited memory. And so again, our goals were to allow multiple programs to be in memory at the same time, protected from one another, and for each one of those programs to have the perception that it had unlimited memory. And so virtual memory is just that. It's memory that does not exist physically, but appears to exist logically to our programs. And so we've talked about the fact that we can break our programs into pages, and we can keep some of those pages in memory, some of those pages on disk. And we're going to use the term, as throughout this discussion, locality of reference. And so what that means is we know that before a program can execute, its instructions and data have to be in RAM. Not on secondary store, but in RAM. And so locality of reference tells us that the next data that's accessed, or the next instruction, is probably going to be residing close to the location of the preceding data or preceding instruction. And so what that tells us is we don't have to bring every single page of instruction for a program into RAM. We just need to bring the ones that are probably going to be used next into RAM. And locality of reference tells us that the page that's going to be used next is probably pretty close to the page that was just used. And so when we try to bring a page in that doesn't exist in the RAM, or when we try and reference a page that doesn't exist in RAM, we have to bring that page in from disk. That's when a page fault occurs. And when a page fault occurs, the operating system has to say, oh, this page isn't in RAM, it's over there on disk, I need to bring it into RAM. And if there's space in RAM available for the page, the process is easy, it just brings it in. But if there's not, then it has to pick a page that's going to move from RAM to disk to make room for the new page. And that's where virtual memory management and demand paging and everything we talked about today is going to come into play. And so here's kind of our overview. We've got our virtual memory, and it's divided up into pages, and every program gets pages within that virtual memory. And then we've got some kind of memory mapping software that's controlling where a virtual memory reference is getting mapped to a physical RAM location. And sometimes we'll make a reference that doesn't exist in RAM. It's out in that secondary store, and that secondary store used to just be disk space, but today it could be flash memory or something. So if it's out there, we've got to bring it in. If there's space available, it's easy. If there's not space available, then we have to pick the space. So we typically divide our virtual memory up into different segments. And our code segments are the program instructions. And so we kind of know the size of that to begin with because we know how big our program file is. Our program uses data to store variables as the program executes. So we have a data section. And then a lot of times we'll have dynamic memory. So we might create a linked list, or we might create a collection in .NET. And so we've got a collection of objects. We store those in the heap. So the heap is kind of our dynamic memory allocation space. And so we see the up arrow on this slide. That just tells us that the heap can grow dynamically as our program executes. So heap space is going to potentially change. Our stack space is where our functions and procedures that we create store variables, they're local variables. And so depending on how our program uses functions and procedures, the stack space is going to differ. So we kind of let it grow down towards the heap. And if the two of these grow to the fact that they run into each other, then a collision occurs, and it's essentially an out-of-memory error that the program's going to have to deal with. And I'm not going to spend too much time on sparse address spaces. Essentially, a sparse address is, let's assume that we have an array. And that array is storing photographs of the stars. And we have billions of stars, and we know that. And we probably don't have billions of photographs yet of stars. We just have lots of stars. And so most of our array locations would be empty because we've not yet gotten a photograph. And so that would be called a sparse data structure because more of the storage locations are empty than more of the locations have actual values in them. And so that's all you need to really know about sparse locations today. Whoops. We've talked about the fact that when we have multiple programs running, we may share memory. And our shared memory may allow them to communicate. And so our shared memory may be the pipe or the channel that they're exchanging messages across. Or it may be some shared values or some shared variables. But to do shared memory with a virtual memory system is we know that our shared memory is probably a physical location in RAM. And we just simply have to map the corresponding virtual address locations for each program to the shared memory. Okay, so the whole concept of virtual memory management is best described and most frequently implemented using demand paging. And with paging, we break our program up into pages. So our instructions have a set of pages, our data have a set of pages, our stack space has a set of pages. Those pages map to physical frames within RAM. For simplicity, we'll use 512 byte pages frames. Keep the size of pages and frames the same, and it simplifies our implementation. And so when we load a program, we're going to load a bunch of instructions and a bunch of data into RAM. So we're going to allocate a bunch of pages. And it's interesting, if you're running Windows, for example, to start the system monitor, you can actually see the system steps that it goes through as it loads a program for the first time. Now, we're not going to load all of the instructions, and we're not going to load all the data. Why? Because locality of reference tells us And you guys need to know for the test and for the midterm and for the final exam the definition of locality of reference. Locality of reference tells us that the next instruction or the next piece of data is probably close to the previous instruction or previous data, so it's probably in the same page. And so with locality of reference and paging, we're only going to bring in those pages that we need at any given time. Now, what that tells us is the operating system needs to know which pages are in memory and which pages are in disk. And to do that, we're going to have a valid bit, which we'll see, which basically says it's not in memory. We need to go get it from disk before we can use it. And so we've talked about the fact that when we run multiple programs in a multi-programming operating system, there's times where we may swap one program out to disk so we can bring a new program in. This just kind of shows the fact that even if in a demand paging environment, when we do that, we're doing that swap operation based on pages. So we don't necessarily have to say, I'm going to move all program A out. I might move 70% of the pages of program A out. And so with demand paging, I have finer granularity of what I move between disk and memory. Now we talked about the fact that when we use paging, part of a program instructions may be in memory, they may be in disk, and part of a program data space may be in memory, may be in disk. We use a valid bit to keep track of is the page that we're trying to refer to in memory or on disk. If it's in memory, we can just use it. If it's on disk, we've got to bring it in from disk. Again, when we bring a page in from disk, if there's available open spots in memory for that page, process is simple. If there's not, we then have to move a page. And this is where our page replacement algorithm falls into place. We have to pick the page that we're going to just toss out. Now we can just say grab any page. Grab the first page you come across. Grab the most recently used page. Grab the least recently used page. All of these are algorithms for our page replacement process. And so it's driven by this valid bit. And because this is a bit, we can do a lot of this in hardware. So we know that we have logical memory, which is the memory references and program instruction references that a program refers to. And so they're probably just offset locations, and wherever they get loaded in RAM, then we need to do some kind of mapping. And so let's take a look here. Our frame 0 corresponds to the fact that page A, and so is in memory, so its valid bit is set to V. If we look at frame 1, it's not in memory. Its invalid bit is set to I. And so if we were to access one of those pages, we'd have to bring it in from disk. So let's take a look at our physical memory for a minute. We've got pages 4, 6, and 9. And sure enough, in our page table, it shows that for pages 4, 6, and 9, all of them have valid bits set. So that tells us that they're all in memory. If we were to access location or page 4, its invalid bit's not set, so we'd have to pull that corresponding page E from disk into memory. So because we're using just a simple bit to say, is it in memory, is it not in memory, we can do this process pretty quickly. When we have a page-driven operating system, there's going to be times where pages reside in RAM and pages don't. When we access a page that's not in RAM, a page fault occurs. And so, again, using the Windows Monitor, you can monitor your page faults. And so the more pages of physical RAM that we have available that the operating system can load things into, the less likely we're going to page fault. So that explains why adding memory to a system normally improves performance. But we're going to learn that there's something called Belady's anomaly that tells us that there's times, given the reference string of pages that a program's trying to access, we can actually incur more page faults by adding memory. And you need to know the definition of Belady's anomaly for your exams. And so this page kind of summarizes what we've been talking about. When we do paging, we're going to use a secondary store. Disk space, flash memory, whatever our secondary store is. Could be tape. And so ideally we're going to have space on there that we're moving things to and from. We'll call that the page file, or we'll call it the swap file. And in a pure demand paging model, we're going to take advantage of the fact that typically the next instruction or the next piece of data is probably close in proximity to the last instruction, last piece of data, locality of reference, to improve our performance and optimization. So let's say that we access an instruction that's not in RAM. The operating system hasn't loaded the corresponding page yet, so it's not in RAM. So we try to access the instruction. The valid bit's not set because the instructions page is sitting out on disk. So everybody says, whoa, we need to load this. The operating system says, okay, I can't have the CPU execute the instruction yet because it's not in memory, so let's go bring it into memory. If there's an available page, great. Use that available page, just load it. If there's not, then we have to do a page replacement. And that's where our page replacement algorithms come into place. We have to pick the page that we're going to pull out of RAM, write to disk, and then move the other page from disk into RAM, and then kind of restart the instruction and try the execution again. And this kind of shows that process of how we try to access an instruction, it's not there, then we have to do a page replacement, bring the page in, and then restart the instruction. So when we think about the performance of demand paging, why do we do this? One, it allows us to easily run multiple programs at the same time. Two, it allows us to give programs the perception that they have unlimited memory. A good thing. So in the past we had, and the past wasn't that long ago, before some of you were born, or most of you were born, but maybe we had 32K of memory, or 64K of memory. Programmers had to constantly worry about managing memory. As virtual memory and things have come on to play, programmers can be sloppier. Let's just say it. They can be sloppier because they don't have to manage memory as well. Because the operating system is going to do it, and virtual memory is going to give programs the perception that they have as much memory as they need. So the more RAM we add, the less often we're at the page fault. Page faults are slow because even if we're using flash memory is slower than RAM. If we're using a disk drive, a secondary store, which most of us are in our PCs, the mechanical nature of disk drives makes them slower. So our paging gives us flexibility. It allows programs to think they got unlimited space, allows programs to reside in RAM at the same time without impacting one another. There's always benefits, but when we have to page and perform a page fault, there's performance issues that start to impact us. So the more that we can improve the performance of our page replacement processing, the better our whole system executes. And this kind of talks about the fact of, okay, how do we determine the impact of a page fault if we have to go to disk, if we have to decide which page we're going to replace, if we have to write that page to disk, then move the other page in, what's the overhead? And so what are some ways that we can optimize our page swapping is, well, one, we need to make a good determination of are there available pages. So the more memory we have, the more likelihood there's going to be available pages, so the less likely we're going to need to swap pages, so the performance is better. Then if we need to swap pages, how can we pick a page quickly so we can get the process moving? Now when we have a page and that page contains data, normally our instructions is just going to be a read-only page. Read the next instruction, execute it. Read the next instruction, execute it. But when we have data, we're writing to those memory locations because we're changing the value of our variables. So we have a choice. We can allow the operating system to change the value of the variables in RAM, and then if we later need that corresponding page, we can write that page to disk. Or we can say, operating system, when you change the value of a variable in a page, I want you to automatically write it to disk, kind of behind the scenes, this background task. That way, should I need to swap this page, I just toss it. I don't need to worry about writing it to disk because I already have. We refer to that process as copy on write. Copy on write exists to try to improve the performance during our page swaps. And so this just kind of shows the process. In this case, we've got two processes. They're sharing pages in memory. They're sharing pages A, B, and C. And so what happens now if process 1 modifies page C? Now, in an ideal world, process 2 would automatically see that update, because otherwise it's updating, accessing page C, and it's not seeing the most recent data. And so now what complexities get added when we start doing on-demand paging? And so if process 1 modifies page C, and then page C gets selected to be moved from RAM to secondary store, we need to know that there's two copies of page C, or there's different copies of page C. So when we have shared memory, we just complicate this whole process. So again, we've talked about the fact that if we need to bring a page in from secondary store into RAM and there's available pages, this process is easy. Just do it. But if there's not, then we need to have a page replacement algorithm. And here's where our page replacement comes. And so we know that there's a valid bit that says whether or not the page is in RAM or the page is in disk. Now we're going to use a modified bit that says, hey, we updated these variables. You need to write this page back to disk before you can get rid of it. Because when the program later needs that page again, we need to have the most current state of the variables. So now we've talked about a valid bit, now we're talking about a modified bit. You should know the purpose of both for the exams. And so here's our kind of our overall picture. We try to access a page. That page is not in RAM, so its validity bit tells us it's not in RAM, which means we have to go out to disk to get it. Now we have to pick a page that we're going to move out of RAM back to disk to make room for our new page. And so we'll actually create for studying purpose something called a reference string, which shows us a sequence of pages that we're trying to refer to. So we can start to talk about how does our reference string impact our performance as we do paging. And so if we don't have an open page, we have to pick a page. So we're going to call it our victim frame in this case. And if the victim frame has been recently updated, we may need to write that page out to disk. And so keep in mind that the virtual memory management and the demand paging is giving us great flexibility. We can have multiple programs in memory that can't muck with each other because they all refer to different pages. And each one of those programs seems like they have unlimited memory. But behind the scenes, we have the overhead of managing those pages, deciding which pages get in memory at any given time. And so our flexibility is matched by complexity, and it's also matched by overhead. So our page replacement algorithm, our demand paging model, our virtual memory model, all has a corresponding overhead which we have to consider. And typically, we can improve performance by getting, first, more memory, so we page less often, and then 2, faster secondary storage, so when we do page, we're doing it as quickly as possible. And so again, this kind of shows us our process. Within our page table, our valid or invalid bit tells us whether or not the page resides in memory or on disk. When we need to swap something out, we pick a victim page using our page replacement algorithm, and we may have to write that page back out the disk if it's recently been changed. And so you can see down here at the bottom, we've got a reference string, and that's just kind of the sequence of pages that a program is referring to. And so in this case, it refers to page 7, page 0, page 1, 2, 0, 3, 0. So you can see that 0 starts to get used quite a bit. If we're picking 0 to move out to disk, you can see just based on our references, we'd be constantly moving 0 back in from disk. So as we decide which pages we're going to replace and swap, it's nice to have some knowledge of these reference strings. Unfortunately, we normally don't have that type of a priori knowledge. So this tells us, compares the number of page or page faults that are occurring based on the number of frames of real memory that we have in RAM. And so again, the more RAM we have, the fewer page faults we're going to incur. And so that's why adding RAM to any system normally improves performance, because in this case we're reducing the number of page faults. That said, there's something called Belady's anomaly that says by adding more frames, more physical RAM, you can sometimes actually, depending on the reference string, incur more page faults. And so it's really counterintuitive. You'd think the more RAM the better, and generally the more RAM the better. But in this case, depending on the reference string, we can actually see that, gosh, by adding more RAM, we screwed things up, we made performance worse. And so I would know the definition of Belady's anomaly for test. And so you should also be able to be given a string of page references and kind of show, based on the page replacement algorithm, what the RAM looks like. So in this case, we're doing a first in, first out page replacement. Pretty simple. Well, how do we know which page was first in or first out? The operating system would have to have some kind of stack or some kind of data structure that's tracking this, so we can decide which page is going to swap in and swap out. And so here's Belady's anomaly. And what does Belady's anomaly tell us? Again, adding more pages, frames of RAM can actually increase the number of page faults. And so in this case, we see that when we went from 3 to 4 frames, we actually increased the number of page faults based on the particular reference string. And so for system performance, when we have to swap a page out, it'd be nice not to swap a page out that's going to be immediately used, because then we have to swap it back in. And so unfortunately, we don't know in advance what page is going to be used. And so locality of reference tells us that the next page or next instruction or next data access is probably going to be located in close proximity to the last one. So that gives us a little bit of hints as to which pages we should start to swap. We want to pick the right page to swap just to improve overall system performance. And so in an ideal case, this is an optimal page replacement. This algorithm knows what we're going to use, which is in reality not something we can do. But it's the optimal page replacement. So we're picking the page that's going to lead to the least number of page faults. And so that's great, but in the real world, we don't know the information that you would need to know to do things optimally. So we could say, okay, I want to use the least recently used page. Okay, well, what does that mean? That from an operating perspective, it has to track for every page? Does it need to know the date and time? If it needs to do date and time processing, and we're really wanting to do this rapidly every time we want to change a page, well, comparing dates and times is a lot of processing overhead, and so that could really start to slow things down. So how do we implement the least recently used? Because the one that we've not used in a while is probably one we won't use for a while. So let's move it out to disk. Cool algorithm, but how do we implement it? Well, sometimes they use a counter, and so each time a frame is used, we increment the counter. And if that's the case, then we can just pick the one whose counter is the lowest, and it's probably least frequently used, and so we can grab it to swap out. So the counter is fast. We can also use a stack data structure to keep track of the frames that were most recently used. Anytime we have to bring a data structure into play, however, we're increasing the complexity, and complexity is going to increase processing time. and we want our memory management to be as fast as possible. And so here's kind of using a stack data structure to move through a reference string. And in preparation to understanding what you need to know for the tests and things, you should walk through some of these algorithms with different reference strings. And so we can have a bit that tracks that a frame was recently used. And so if the bit's set to 1, it was recently used, don't grab it. And then periodically we can refresh everything back to 0. So we've got multiple things going on, but this may be a fast way, so we don't have to do date and time comparisons to determine which one of our memory frames are being used on a regular basis. We could store clock information, but again, we're increasing the amount of processing that has to occur on every page fault. And we want those page faults to be fast. So a lot of times using counters becomes a good solution, and we can periodically reset the counters just to keep things real. And then, again, to improve performance, we may have an application that has a fixed number of pages in its working set. But gosh, it'd be nice because this application is really plugging along if we could pre-buffer some of those pages and things. So there's different ways that we can improve the underlying performance when we have to do a page replacement. Now, we know when we're replacing a page and we have to move a page, we have to write that page to disk. And so typically in disk, we'll have a page file or a swap file. And we may just do a raw data mapping of offset locations to improve the performance, overall performance of the page swap process. And again, this is kind of showing us the amount of overhead that we would incur and trying to make a determination of what's the best way to approach this from a processing perspective to improve the optimization of a page fault operation. And so there's different algorithms that we can use, from least recently used, most recently used, a priority-based algorithm, in order to improve the performance of our virtual memory management. And why do we want to do this? Because our virtual memory management runs behind the scenes with every program. So we want to have it as fast as possible. And then we can actually say, do we have one scheme, one mechanism that we use across all applications that are running? Or does each process have its own set of allocated frames and its own process for determining which pages and frames are swapped in and out next? And I want to put a bug in the back of your head that you think about, not necessarily so much that you're trying to solve it, but what if we use different memory types? Then we can't use the same memory management system. So here we've got a job that's running on different processors, so it's got different memory types. Now how do we do the virtual memory management across that? So you can start to see how things like NUMA, non-uniform memory access, starts to become just complexity. That complexity is going to lead to overhead. And we've talked about the fact that when you run multiple programs at the same time, the operating system may have to move one program out from RAM to disk so another can run. And if this process occurs over and over, we have thrashing. And thrashing just increases the system overhead. So our goal is to reduce thrashing. Well, we can have the same situation occur depending on the number of physical memory RAM frames that we have and the amount of paging that we're having to do. So the system can spend all its time moving pages in and out of memory to disk and performing a little work. And this is where you see your disk drive light up on your system. And we'll refer to this whole process as thrashing. And so in this case, the number of programs we're trying to run at the same time increases thrashing, which increases overhead, which decreases our CPU utilization. Now here's just kind of a graphic that shows instructions that are being accessed and data that's being accessed, and you can see how they're all kind of in similar locations. This is our locality of reference. All locality of reference means, you need to know this definition, is the next instruction or next data access is likely to be close in proximity to the previous instruction or previous data access. So as you look at these memory allocation schemes, you'll encounter the term working set. And we talked about the fact that every program has a set of related pages that it's working with. That is the program's working set. And so for simplicity, we can say that all programs get the same number of pages, so they all have the same working set. Or this program's a higher priority, so it gets a greater working set. Or this program tends to page a lot, so let's give it a bigger working set. The working set is the set of pages that the program's currently utilizing. And we want to allocate working sets in such a manner to reduce the number of page faults. And this kind of shows the working set size and how it starts to impact pages, giving a page reference string. And so behind the scenes, our operating system has to track working set size. And again, it could allocate the same working set to everybody. That's pretty simple. But every program has a different processing characteristics, so kind of customizing the working set makes sense. And so by getting the working set right, our goal is to reduce the number of page faults. And so we know that when we have a file resides out on disk. And when we have to read and write that file, we typically do so using file pointers and different operations. Because we have this paged memory system, a lot of operating systems will implement something called memory map files. And a memory map file is just kind of a file that we page in and out of. So if I need the first byte, I need the first page in. If I need the 513th byte, I need the second page in. And so we use kind of a virtual memory approach to accessing files. And that's all a memory map file is. And so with the memory map file, we can perform all of our common operations. We can open the file, we can close the file, we can read the file, we can write to the file. And we just keep track of locations within the file, offsets, as well as the page location. And then we can load the file into memory, and typically if we've got a fast virtual memory management system, then treating files as memory mapped also has fast performance. And again, this shows us the file on disk being broken up into pages, and within each page we'd have byte offsets of specific memory locations. And so memory map files are a simple way for us to share information across processes. And so just kind of wrap things up, based on locality of reference, we know that the next instruction or the next piece of data that we use is probably going to be close to the last instruction or the last piece of data that we used. If we're getting close to the end of a page, we can bring the next page in advance, pre-paging. So when we actually get to the instruction or data, it's already in RAM, so things are good. Again, we can reduce the number of pages that we need by increasing the page size. That probably increases the likelihood that we'll have pages or locations in memory because we've got a larger page size, but also increases then it takes longer to read and write the pages from disk because they're just bigger. And we may have some locations on a page that we don't ever use, so then fragmentation occurs. So we have to try to decide what's a good page size and then go with it. And typically we'll go with 512 bytes. And again, we talked about last time when we looked at memory management, we've got a virtual address. We have to translate that virtual address into a physical address. And so we'll use the translation look-aside buffer to try to reduce the overhead of doing that for every memory reference. And then finally, how we create our code impacts how we access virtual memory. So we want to think about the fact that we've got this underlying virtual memory mechanism as we start to optimize and design our code. And so I'm going to leave it there, and I'll open it up for any questions. And I'm going to stop recording so we can save this recording, and then I won't record your questions.